Okay, those are, that's so to speak, the text for today. The Fourier series and the Fourier expansion for f of t. So f of t, if it looks like this, should be periodic with periodic, and 2 pi should be a period. Sometimes people rather sloppily say periodic with period 2 pi, but that's a little ambiguous. Since this period could also be pi or a half pi or something like that, just as well. The ANs and BNs are calculated according to these formulas. Now, we're going to need in just a minute a consequence of those formulas, which it's not subtle, but it's because there are formulas for AN and BN, it follows that that once you know f of t, the ANs and BNs are determined. Or to put it another way, a function cannot have two different Fourier series. Or to put it yet another way, if f of t, if two functions are equal, you'll see why I write it in this rather peculiar form, then their Fourier series for f is the same as the Fourier series for g. And the reason is because if f is equal to g, then this integral with an f there is the same as the integral with g there, and therefore the ANs come out to be the same. And the same way the BNs come out to be the same. So the Fourier series are the same coefficient by coefficient for f and g. Now, my ultimate goal, let's all put down the argument since there are formulas, since we have formulas for AN and BN. Now, a consequence of that is, well, let me first say, what I'm aiming at is, you'll be amazed at how long it's going to take me to get to this. I just want to calculate the Fourier series for some rather simple periodic function. It's going to look like this. So here's pi, and here's negative pi. So a function which just looks like t in between those two. So it goes up to, it's the function t more or less, goes up to pi here, minus pi there. But of course it's got to be periodic, a period 2 pi. Well, then it just repeats itself after that. So after this it just does that and so on. It's a little ambiguous what happens at these endpoints. Oh, let's not worry about that for the moment. And frankly, it won't really matter because the integrals don't care about what happens at individual points. So there's my f of t. Now, I, of course, could start doing it right away. But you'll quickly find, if you start doing these problems and hacking around with them, that the calculations seem really quite long. And therefore, in the first half of the period, I want to show you how to shorten the calculations. And in the second half of the period, after we've done that and calculated this thing successfully, I hope, I want to show you how to remove various restrictions on these functions, how to extend the range of Fourier series. Well, for one obvious thing, for example, is suppose the function isn't periodic of period 2 pi. Suppose it has some other period. Does that mean there's no formula? Well, of course not. There's a formula. But we need to know what it is. Particularly in the applications, the period is rarely 2 pi. It's normally 1 or something like that. But let's first of all, I'm sure what you'll appreciate is how the calculations can get shortened. Now, the main way of shortening them is by using evenness and oddness. And what I claim is this, that if f of t is an even function, remember what that means, that f of negative t is equal to f of t. Cosine, a good example, of course, is cosine nt. All these functions are even functions. If f of t is even, then its Fourier series contains only the cosine terms. In other words, half the calculations you don't have to do if you start with an even function. That's what I mean by shortening the work. There are no odd terms, no sine, or let's put it positively, all the bn's are 0. All the bn's are 0. Now, one way of doing this is would be to say, well, if the bn, why the bn 0? Well, we got formulas, and fool around with the formula for the bn and think about it a little bit and finally decide that that has to come out to be 0. That's not a bad way, and it would remind you of some basic facts about integration, about integrals. Instead of doing that, I'm going to apply my little principle that if two functions are the same, then their Fourier series have to be the same. So the argument I'm going to give is this. So I'm going to try to prove this statement now, and I'm going to use the facts on the first board to do it. So what is f of minus t? Well, if that's equal to f of t, then in terms of the Fourier series, how do I get the Fourier series for f of minus t? Well, I take the Fourier series for f of t and substitute t equals minus t. Now, what happens when I do that? So the Fourier series for this looks like a0 over 2 plus summation what? Well, the an cosine nt, that does not change, because when I change t to negative t, the cosine nt does not change, stays the same, because it's an even function. What happens to the sine term? Well, the sine of negative nt is equal to minus the sine of nt. So the other terms, the sine terms, change sign. So all that's the result of substituting t for negative t in f of t. On the other hand, what's f of t itself? Well, f of t itself is what happened before that. Now it's got a plus sign because nothing was done to the series. Well, if the function is even, then those two right-hand sides are the same function. In other words, they're like my f of t equals g of t. And therefore, the Fourier series on the left must be the same. In other words, if these are equal, therefore these have to be equal too. Now, there's no problem with the cosines terms. They look the same. On the other hand, the sine terms have changed sign. Therefore, it must be the case that bn is always equal to negative bn for all n. That's the only way this series can be the same as that one. Now, if bn is equal to negative bn, that implies that bn is 0. 0 is the only number which is equal to its negative. And so by this argument, in other words, the uniqueness, using the uniqueness of Fourier series, we conclude that if the function is even, then its Fourier series can only have cosine terms in it. Now, you say, hey, that's obvious. Cosine, that's just a point of logic, but this is a mathematics course after all. It's not just about calculation. Many of you would say, yeah, of course that's obvious because cosines are even and the sines are odd. I say, yeah, and so why does that make it true? Well, if cosine is even, plug t into minus t, and, what you're proving is the converse. The converse is obvious. Yeah, obvious. I don't care. If the right-hand side is a sum of even functions, well, so is the left. But I'm saying it the other way around. If the left is an even function, why does the right-hand side have to have only even terms in it? And this is the argument which makes that true. Now, there's a further simplification, because if you've got an even function, oh, by the way, of course, the same thing is true for the odd. I ought to put that down. So also, if f of t is odd, then I think one of these proofs is enough. The other you can supply yourself. And that will imply that all the ANs are 0. Even including this first one, A0, and the reasoning by the same reasoning. So, an even function uses only cosines in its expansion, Fourier expansion. An odd function uses only sines. Good. But we still have to, well, suppose we got an even function. We still got to calculate this integral. Well, even that can be simplified. So the second stage of the simplification, again, assuming that we have an even or odd function. And by the way, totally unauthorized. So, if f of t is even, what we'd like to do now is simplify the integral a little. And there's an easy way to do that, because look, if f of t is an even function, then so is f of t cosine nt is also even. Right? Imagine we could make little rules about, an even function times an even function is an even function. There are general rules of that type, and some of you know them, and they're very useful. But let's just do it ad hoc here. If I change t to negative t here, I don't change the function because it's even, and I don't change the cosine. So because that's even, so if I change t to negative t, I don't change the function. Either factor that function, and therefore I don't change the product of those two things either. So it's also even. Now, what about an even function when you integrate it? Here's a typical looking even function. Let's say something like, I don't know, like wiggle, again. Here's our better even function. All right. So the minus pi to pi. Even. Even though the t-axis is somewhat curvy. So there's an even function. The point is that if you integrate an even function from negative pi to pi, I think you all know even from calculus you were taught to do this simplifications. Don't do that. Instead, integrate from 0 to pi and double the answer. Why should you do that? The answer is because it's always nice to have 0 as one of the limits of integration. I take trust to your experience. I don't have to sell that. Minus pi is a particularly unpleasant lower limit of integration because you're sure to get in trouble with negative signs. There are bound to be at least 3 negative signs floating around, and if you miss one of them, you'll get the wrong size of answer. The answer will have the wrong sign. So the way the formula from this simplifies is that an, instead of integrating from negative pi to pi, I can integrate only from 0 to pi and double the answer. So our better formula is this. If the function is even, this is the formula you should use. 0 to pi f of t cosine nt dt. Of course, I don't have to tell you what bn should be, because bn will be 0. And in the same way, if f is odd, the same reasoning shows that bn, of course, an will be 0 this time, but it will be bn that will be 2 over pi times the integral from 0 to pi of f of t sine nt dt. Maybe we better just say a word about that, since why is that so? If it's odd, doesn't that mean things become zero? You know, if an odd function, you integrate an odd function like that, the integral over a minus pi to pi, you get 0. Well, but this is not an odd function. This is an odd function, and this is an odd function, but the product of two odd functions is an even function. Odd times odd is even. I said I wasn't going to give you those rules, but since this is the one which trips everybody up, maybe I better say it, just because it looks wrong. Right? This is odd. That's odd. Think about it. If I change t to negative t, this multiplies by minus 1. This multiplies by minus 1. And therefore, the product multiplies by minus 1 times minus 1. In other words, it multiplies by plus 1. Nothing happens. So it stays the same. Why is this? Does nobody believe this, even though it's true? It's because they're thinking about numbers. Everybody knows that an odd number times an odd number is an odd number. So I'm not multiplying numbers here, so I'll put them in boxes to indicate that they're not numbers. How's that? A brand new invented notation. The box means caution. These are what's inside is not a number. It's the word odd or even. It's just a symbolic statement that the product of an odd function and an odd function is an even function. Even times even is even. What's odd times even? Odd, yes. It has to get equal time, obviously. Something must come out to be odd, right? Okay, so now that we've got our two simplifications, we're ready to do this problem. Instead of attacking it with the original formulas, we're going to think about it and attack it with our better formulas. So now we're going to calculate the Fourier series for f of t. The first thing I see, so f of t is our little thing here. Well, first of all, what kind of function is it? Odd, even, or neither? Most functions are neither, of course. But fortunately, in the applications, functions tend to be one or the other, or they can be converted into one to the other. Maybe if I get a chance, I'll show you a little how, or the recitations will. So this function is odd. Okay, half the work just disappeared. I don't have to calculate any ANs. They will be 0. So I only have to calculate Bn, and I'll calculate them by my better formula. So it's 2 over pi times the integral from 0 to pi. And what I have to integrate, well now, finally, you've got to integrate something. From 0 to pi, this is the function t. So I have to integrate t times sine of nt dt. Okay. So this is why you learned integration by parts. One of many reasons why you learned integration by parts, so that you wouldn't have to pull out your little calculators to do this. Okay, now let's do it. So it's 2 over pi. Let's salt that away so we can forget about it. And what's then left is just the evaluation of the integral between limits. So if I integrate by parts, I'll want to differentiate the t and integrate the sine, right? So the first step is you don't do the differentiation. You only do the integration. So that integrates to be cosine nt over n, more or less. The only thing is if I differentiate this, I get negative sine nt instead of, so I want to put a negative sign in front of all this. And I will evaluate that between the limits, 0 and pi, and then subtract what you get by doing both things, both the differentiation and the integration. So I subtract the integral from 0 to pi of, I now differentiate the t and integrate. Well, I just did the integration. That's negative cosine nt over n. You see how the negative signs pile up? And if this is negative pi instead of 0, it's at that point one starts to lose heart. You know, you see 3 negative signs, and then when you substitute, you're going to have to put in still something else negative, and you just have the feeling you're going to make a mistake. And you will. So, okay. Now all we have to do is a little evaluation. Let's see. At the lower limit, I get 0 here. So let's write it right away as 2 over pi. At the lower limit, I get 0. That's nice. At the upper limit, I get minus pi over n times the cosine of n pi. Now, once and for all, the cosine of n pi, if you like to make separate steps out of everything, okay, I'll let you do it this time. But in the long run, it's good to remember that that's negative 1 to the nth power. The cosine of pi is minus 1. The cosine of 2 pi is plus 1. 3 pi minus 1, and so on. So, here, so at the upper limit we get minus pi over n times, oh, I didn't finish the calculation, times the cosine of n pi, which is minus 1 to the nth power. And now how about the other guy? Should we do it in our heads? Well, I can do it in my head, but I'm not so sure about your heads. Maybe just this once we won't. So what is it? It's plus sine nt, right? So I combine the two negative signs to a plus sign by putting one this way and the other one that way. And then so it's, if I integrate that now, it's sine nt divided by n squared, right? And that's evaluated between 0 and pi, and of course, the sine function vanishes at both ends, so that part is simply 0. And so the final answer is that Bn is equal to, well, the pi's cancel. This minus combines with those n to make one more, and so the answer is 2 over n times minus 1 to the n plus first power. And therefore, the final result is that our Fourier series, the Fourier series for f of t, that funny function is, the Fourier series is summation Bn, which is 2, put the 2 out front because it's in every term, there's no reason to repeat it, minus 1 to the n plus first power over n times the sine of nt. That's summed from 1 to infinity. Let's stop and take a look at that for a second. Does that look right? Okay, here's our function. There's a function. What's the first term of this? When n is 1, this is plus 1. 1. So the first term is sine t. What's the next term? Minus, when n is 2, this is negative. So it's minus 1 to the third power. So that's negative 1 over 2. So it's minus 1/2 sine 2t. And then it obviously continues in the same way. Plus a third sine 3t. Now, watch carefully, because what I'm going to say in the next minute is the heart of Fourier series. I've given you that visual to look at to try to reinforce this into you, but it's really very important that you go to the terminal yourself and do that work, simple as it is, and pay attention now. Now, if you think old-fashioned, i.e., if you think Taylor series, you're not going to believe this, because you will say, well, let's see, these go on and on. Obviously, it's the first term that's the important one. That's 2 sine t. Now, the derivative 2 sine t would exactly follow the pink curve. Sine t would look like this. 2 sine t goes up with the wrong angle. The first term, in other words, does this. It's going off with the wrong slope. Now, that's the whole point of Fourier series. Fourier series is not trying to approximate the function at 0, at the central starting point, the way Taylor series do. Fourier series tries to treat the whole interval and approximate the function nicely over the entire interval, in this case, minus pi to pi, as well as possible. Taylor series concentrates at this point, does it the best it can at this point, then it tries to, with the next term to do a little better, and then a little better. The whole philosophy is entirely different. Taylor series are used for analyzing what a function looks like when you stick close to the base point. Fourier series analyze what a function looks like over the whole interval. And to do that, you should therefore aim to, so the first approximation is going to look like that. Going to have entirely the wrong slope, but the next one will subtract off something which sort of helps to fix it up. I can't draw this, that's why I'm sending you to the visual, because the visual draws them beautifully. And shows you how each successive term corrects the Fourier series and makes it, the sum, a little closer to what you started with. So the next guy would, let's see, it's 2t, so I'm subtracting off, it probably, I'm just guessing, but it probably ends up looking, I don't dare draw this. I haven't prepared to draw it, and I know I'll get it wrong, so, okay, your exercise. But it'll look better. It'll go maybe something like, let's see, it has to end up there, so all that gets, some of it's subtracted off, and I don't know. I don't know what it looks like. When you use the visual at the computer terminal, notice I've asked you to use it 3 times on a variety of functions. I think this is maybe even one of them. Notice that you can set the parameter, you can set the coefficients independently. In other words, you can go back and correct your works, improving the earlier coefficients, and it won't affect anything you did before. So but the most vivid way to do it is to try to get visually, by moving the slider, to try to get the very best value for the first coefficient you can, and look at the curve, then get the very best value for the second coefficient and see how that improves the approximation, and the third, and so on. And the point is, watch the approximations approaching the function nicely over the whole interval instead of concentrating all their goodness at the origin, the way a Taylor series would. Now, there's still one mathematical point left. It's that equality sign, which is wrong. Why is it wrong? Well, what I'm saying is that if I add up this series, it adds up to f of t. Now, it almost does, but not quite. And I better give you the rule, the theorem. Of all the theorems in this course that aren't being proved, this is the one that would be most outside the scope of this course. So the one which I would most like to prove, in fact, just because I'm a mathematician, but wouldn't dare. The theorem tells you when a Fourier series converges to the function you started with. And the essence of it is this. If f is continuous, is a continuous function at, let's give the point, it's confusing just to keep calling it t. If you like, call it t, but I think it would be better to call it t0, just to indicate I'm looking at a specific point. So if the function is continuous there, then f of t, the value of f of t, is equal to, the Fourier series converges, and it's equal to its Fourier series. the sum of the Fourier series at t0. And the fact that I can even use the word sum means that the Fourier series converges. In other words, when you add up all these guys, you don't go to infinity or get something which just oscillates around crazily. They really do add up to something. Now, if f is not continuous at t0, this emphatically will not be the case. It will definitely not. But by far the kinds of discontinuities which occur in the applications are ones like in this picture where the discontinuities are jump discontinuities. They're almost always jump discontinuities. And in that case, in other words, they're isolated. The function looks good here and here, but there's a break. Typically, electrical engineers just don't leave it gap because they like, I don't know why, but they were, an electrical engineer and others of his or her ilk would write that would draw that function like this, like a ripsaw tooth. Even those vertical lines have no meaning whatever, but they make people look happier. So if f it has a jump discontinuity, at t0, and as I said, that's the most important kind, then f of t, then the Fourier series adds up to, converges to, it converges to the midpoint of the jump. Let me just write it out in words like that. The midpoint of the jump. That's the way we'll be using it in this course. There's a notation for this, and it's in your book. But those of you who would be interested in such things would know it anyway. So let's just call it the midpoint of the jump. So if I ask you to what does this converge, in other words, the series, what this shows is that this series twice, I'll write it out in the abbreviated form, summation minus 1 to the n plus 1 over n sine nt. What's the sum of the series? What is it? Let's call this not little f of t. Let's call it capital F of t. I want to know what's the graph of capital F of t. Well, the initial thing is say, well, it must be the same as the graph of the function you started with. And my answer is almost, but not quite. Almost, but not quite. In fact, what will its graph look like? Well, regardless of what definition I made for the endpoints of those pink lines, this function will converge to the following. From here to here, I'll draw it. I won't put in the minus pi. I'll leave that to your imagination. So there's a hole at the end here. In other words, the end of this line is not included. And the end of this line, regardless of whether it was included to start with or not, it's not now. And here, similarly, I start up here with a hole and then go down like parallel to the function t, slope 1. And now how do I fill in? So the missing places, this is the point pi, this is the point negative pi, and there are similar points as I go out. Well, since the function's continuous here, the Fourier series will converge to this orange line. But here there's a jump discontinuity, and therefore the Fourier series, this function, converges to the midpoint of the jump, in other words, to here. This function, in other words, converges to this very discontinuous looking function, and rather odd how these points are isolated. But in this case, I can prove to you that it converges here by calculating it. Look, this is the point pi. What happens when you plug in t equals pi? You get every one of these terms is 0, and therefore the sum is 0, so it certainly converges, and it converges to 0. Now, that's a general theorem. It's rather difficult to prove. You would, again, have to take an analysis course. But I don't even get to it in the analysis course in which I teach. So if I had another semester, I'd get to it. But, well, can't do everything. Anyway, we're not going to get to it this semester, to your infinite relief. But you should know the theorem anyway. People will expect you to know it. Well, that was half the period, and in the remaining half, you're going to stay a long time today. Okay, no, don't panic. I have to extend the Fourier series. Okay, let me give you the hurry-up version, indicating the two ways in which it needs to be extended. Extension number 1. The period is not 2 pi, but 2 times, I'll keep the tube just to make the formulas look as similar as possible to the old ones. The period, let's say, instead of 2 pi, is 2 times L. Now, I think you know enough mathematics by this point to sort of, I hope you can sort of shrug and say, well, you know, isn't that just kind of like changing the units on the t-axis? You know, you're just stretching. Yeah, right. All you do is make a change of variable. Now, should we make it nicely? I think I'll give you the final answer, and then I'll try to decide while I'm writing it down how much I'll try to make the argument. First of all, if the period, the main thing to get is, if the period is not pi but L, what are the natural versions of the cosine and sine to use? Use the natural functions. Natural has no meaning, but it's psychologically important. In other words, what kind of function should replace that? The cosine of, I'll certainly have a t here. What do I put in front? I'll keep the n also. The question is, what do I fix? What should I put here in between in order to make the thing come out so that it has period 2L? You probably should learn to do this formally as well as just sort of psyching it out and taking a guess or memorizing the answer. If this is the t-axis, here is t and L, 0 and L. What you want to do is make a change of variable to the u-axis where you keep the axis is the same. This is still the point, but L now in the u, on the u coordinate has the name pi. Now so I'm just describing a scale, a change of variable on the axis. What's the one that does this? Well, when t is L, u should be pi. So t should be L over pi. When u is pi, t is L, and vice versa. How about u expressing u in terms, well, then u is equal to pi over L times t. That's the backward form of writing it, or the forward form, depending upon how you like to think of these things. Okay, so the cosine should be pi over L times t, in order that when t be L, it should be like cosine of n pi, which is what we would have had, which is what, all right, anyway. So if t is equal to L, in other words, where is this function? We want, what am I trying to say? That's the function. This one's probably a little easier to see. Where is this one 0? The sine functions that we used before was 0 at 0, pi, 2 pi, 3 pi. Where is this one 0? It's 0 at 0. When t is equal to L, it's 0. when t is equal to 2L. So this is the right thing. So it's 0. It's periodic, and it's 0 at 0 plus or minus L plus or minus 2L. And in fact, formally, you can verify that it's periodic with period 2L. So in other words, we want our Fourier expansion to use these functions as the natural analog of what would be up there. So the period of our function is 2L, and the formula is, I'll give you the formula, it's f of t equals identical summation an, except you'll use these as the natural functions instead of cosine nt and sine nt. So n pi t over L plus bn, okay, I'm tired, but I'll put it in anyway, n pi t over L. Yeah, but of course, but what about the formulas for an? Somebody up there is watching over us. Here are the formulas. They are exactly what you would guess if somebody said, produce the formulas in 10 seconds, and you better be right. And you didn't have time to calculate. You say, well, it must be wherever I saw, since, let's do the cosine series. Okay, let's do all right, let's not do a cosine series. So it's 1 over L times the integral from negative L. In other words, wherever you see an L, wherever you see a pi, just put an L, times the f of t cosine. And now we'll use our new function, not the old one. I submit that's an easy, if you know the first formula, then this would be an easy one to remember. All you do is change pi to L everywhere, except you got to remember this part. Make it a function periodic of period 2 L, not 2 pi. And similarly, Bn is similar. Looks just the same way. And how about, and the same even odd business goes too, so that if f of t, for example, is even and has period 2L, then the function, then the an, the best formula for the an will not be that one. It will be 2 over L, and where you integrate only from 0 to L, f of t cosine nt dt. So now the bn's will be 0, and you'll just have positive, etc. Similar, so etc. for odd. As I say, this is an important case, particularly if the period is 2. In other words, if the half period is 1, because in the literature frequently 1 is used as the standard normal reference, not pi. Pi is convenient mathematically because it makes the cosines and sines look simple, but in actual calculation it tends to be where L is 1. So usually you have a pi here, you don't have just nt. Well, I should do a calculation, but instead of doing that, let me give you the other extension. Fortunately, there are plenty of calculations in your book. So let me give you in the last couple of minutes the other extension. This is going to be a very important one for us next time. Typically in applications, well, I mean, the first thing, say, well, periodic functions are nice, but, let's face it, most functions aren't periodic. I have to agree. So all this theory is just about periodic functions? No. It's about functions, really, it's about functions where the interval on which you're interested in them is finite. It's a finite interval. Not functions which go to infinity. For those, you'll have to use Fourier transforms. Fourier transforms, not Fourier series. But if you're interested in a function on a finite interval, then you can use Fourier series even though the function isn't periodic, because you can make it periodic. So what you do is, if f of t is on, let's take the interval from 0 to L. That's a sample finite interval. I can always change the variable to make it the interval from 0 to L. I could even make it from 0 to 1, but that's a little too special. It'd be a little awkward. So a function is defined on a finite interval. The way to apply the Fourier series to it is make a periodic extension. And now, since I have so little time, I'm just going to get away with murder by just drawing pictures. So let me give you a function. Here's my function defined on 0 to L. Colored chalk, if you please. Let's make it the function t squared. And let's make L equal to 1. That function is not periodic. If I let it go off, it would just go off to infinity and never repeat its values except on the left-hand side. But I'm not even going to let it be on the left-hand side. It's only defined from 0 to 1 as far as I'm concerned. Okay, that function has an even periodic extension. And its graph looks like this. Extended to be an even function. Okay, now that means from 0 to negative L, you've got to make it look exactly as it looked on the right-hand side, otherwise it wouldn't be even. And now what do? Well, now I've got from minus L to L, so all I am allowed to do is keep repeating the values. Ta-da! In other words, apply the theory of Fourier series to this guy, use a cosine series because it's an even function, and then everything you want to do, you say, okay, all the rest of this is garbage. I only really care about it from here to here. And that's what you'll plug into your differential equation on the right-hand side. Just that part of it, just this part of it. How about the odd extension? What would that look like? Okay, the odd extension, here I start like this. And now, to extend it to be an odd function, I have to make it go down in exactly the same way it went up. And what do I do here? I have to make it start repeating its values, so it will look like this. So the odd extension is going to be discontinuous in this case. And what's the Fourier series going to converge to? Well, in each case, to the average, to the midpoint of the jump. And the odd extension looks like this, and this will give me a sine series. Okay, you got lots of problems to do.